We're going to talk about GTO play, exploitative play, and then we'll take a look at this in cash games, and then we'll take a look at it in tournaments. Here we have our hands. As this slides up, we play more hands. As this slides down, we play fewer hands. The same with villain hands, more hands, fewer hands. And then here is the expectation value of decisions, negative EV land, plus EV land. Here we have payout pressure and then hiding payout pressure. So we're going to start with just a cash game view where we don't have payout pressure. And we also can refer to a situation like this as chip EV in tournaments where there is very little payout pressure, that it's very close to cash games. Okay, so let's talk about game theory optimal first. Let's say we find ourselves in a situation in which the game theory optimal, and we'll talk about what that is just so everybody's clear in a moment. But let's say a Nash equilibrium exists like this. We're supposed to push this many hands, and villain is supposed to call this many hands. And this is our expectation value. Let's say it's right here for this situation. Now, in this case, we can lock our strategy right here. We'll have this expectation value. Now, if the villain changes his strategy in any way, let's say he starts calling with this many hands, our EV is never going to drop below this amount. It'll start to move up like this as our villain deviates away from his GTO strategy. And if he starts calling fewer hands, it's the same thing, our EV increases. As he gets back to his GTO calling range, our EV gets back to its base. So in cash games or chip EV, we have an EV base here at our GTO pushing strategy, and we're always guaranteed to stay there. Now, if the villain goes away, our expectation value will slide up a little bit as he goes up or down. But now let's talk about exploitative strategy. So let's say that our villain gets a little tighter, and he's only calling with this many hands. Well, our EV might slide up to here. Now we can decide to stay at this GTO base, or we can decide to respond to his strategy that's calling with too few hands. And when we talk about max exploitative strategy, it looks like this. We respond by pushing all of our hands. And now our EV could come up to here. So we have the decision. We can stay at our EV base with our GTO pushing range, or we can respond to villains' inaccurate play and push all of our hands. And in return, we get a much higher EV than where we were. So in exploitative play and max exploitative play, we get these large oscillations in our range. When villain calls with too few hands, we're pushing more. If he calls with too many hands, then we push way less. But the point I want to make here is that at this Nash equilibrium, if we stay where we are, we have a base EV, and we never enter this negative EV land. No matter what our villain does, he can't make our EV go any lower. And now let's introduce payout pressure. So in chip EV or cash games, our payout pressure is 0. One chip is worth $1, and that doesn't change. But throughout a tournament, payout pressure increases. And then when we get around the bubble and we get at the final table, payout pressure can be very high, and this impacts decisions dramatically. Now we see something remarkable and very important for a tournament player. So we'll take our same situation. This is our Nash equilibrium for a hero and villain. And so it folds around to us. We're in the small blind again, and we're going to be pushing. And this is what the GTO, this Nash equilibrium, exists for this payout pressure. And now the villain decides to call more frequently. If we stay at this Nash equilibrium and continue to push all these hands, our EV comes down here. So now we find ourselves in a spot where the villain, based on his change in strategy, can give us a negative EV decision. Now, how is this possible? It's because in a tournament, the expectation value of a decision isn't only between us and villain. We have all the other players in a tournament who are impacted by whether or not we're still in the tournament and how many chips we have. So what's happening here is villain, by calling with more hands, is giving away our equity in the tournament and his equity in the tournament to other players. So what does this mean? It means we can no longer camp out here at our Nash equilibrium pushing range. When villain changes, if we're going to stay in plus EV land, we have to adjust our strategy. We can't just have one push-fold chart and follow it. We have to be very aware of where our payout pressure is and then what our villain's strategy is. Because if we're not, we can end up in negative EV land, even though we're following a Nash equilibrium strategy. And this is why following a push-fold chart in a tournament can have you lighting money on fire. When we're in a cash game or we're in a chip EV situation, adjusting to our villain's strategy is a luxury. We can go from a base EV that's always plus EV to a much higher EV. However, in a tournament with payout pressure, adjusting is a necessity. Now, for those of us who know we must adjust to villain strategy, the question needs to be answered, how much do I need to adjust to villain strategy? And what we hear, correctly so, is that if a villain is playing too many hands, we have to be tighter. Now, how much tighter? Do we go to playing no hands? Do we go to playing this many hands, this many hands? How much tighter do we have to adjust? I've not seen anyone answer this question clearly, and in the all-in equity method, we'll teach you how to know exactly how much to adjust. And conversely, we've heard that when our villain leaves the Nash equilibrium and plays fewer hands, we're supposed to push more hands. How many more hands? Are we supposed to push them all? Are we supposed to adjust this much, this much? I've not seen anyone lay out how we can know how much we need to adjust our strategy. We can use Locknode in software and see our ranges, but I'm going to teach you how to do this at the table in your head in seconds. So let's go over to Card Runner's EV software. I'll show you this in real time. So here you can see we're in a cash game. I've had the software run the Nash equilibrium strategy. Here's what the small blind should push. Here's what the big blind should call. So take a look at our small blind strategy. It's at 4.47. The big blind's 5.53. Because we're in a cash game, as the small blind, we can camp out here and we'll always have a minimum of 4.47 EV, no matter what the big blind does. So let's change his strategy. Right now he's calling with 52% of hands, and let's say he gets looser than that and he goes to 72. And you can watch the EV of our strategy of continuing to push goes up to 5.28. It raised slightly because the villain left the Nash equilibrium. Now we'll reduce his calling hands to maybe he's only calling 33 instead of his 52. We'll run the EV again, and you can see we're above the 4.47 base we had. Now let's maximally exploit the villain's overly tight calling strategy. And instead of pushing 71% of our hands, we're going to push them all. And you can see the EV of our strategy is now 7.28. So by maximally exploiting our strategy, we won a lot more money. Now let's go back to where villain is calling with too many hands. And now if we push all of our hands, you see that we've dropped below our 4.47 base. I've allowed the software to figure out that our best strategy is now to push fewer hands, around 60% of our hands. And when we do that, we see again that we're able to increase the EV of our strategy to 7.56. So again, the Nash equilibrium of this strategy in a cash game is 71% pushing, 52% calling. But now let's change this to a tournament. We're going to input a prize structure. We can keep this 50, 30, 20. We'll put two more players in the tournament who have two big blinds. We'll put two more players in the tournament who have 10 big blinds. So now there are 6 players in this tournament. We have a prize structure of 50, 30, 20. So we have some payout. We have some payout implications. Based on these payout implications, we'll see our push-fold strategies. We'll see our push and call strategy percentages change. Now the Nash equilibrium strategy is 88% and our villain is supposed to call 27%. But notice here that at the Nash equilibrium we have 0.24 for the small blind. So remember, 0.24 negative 0.41. Now we're going to make our villain call, say, with 40% of hands instead of the 27% in this Nash equilibrium. We'll stay at 88. And look what happened. The villain's change turned us into a negative EV push. If we continue to follow a push-pull chart in this scenario and we don't adjust to the changes in the big blind strategy, we can end up with negative EV decisions. Now, what should our range look like here, based on the villain calling with 12% more hands? Let's find out. So here's our range now. But how are we supposed to be able to do this at the table? I'll show you how. You'll be able to figure this out in your head at the table in seconds. And what if the villain instead is too tight? And instead of 27% of hands, he's going to play, let's call it 20. Now, if we stay at our pushing range of 88.2, we are plus EV, it's 0.78. And this has gone up a little bit because villain is folding more frequently and so giving us the pot more often. And if we want to exploit this more, how many more hands should we push? Let's find out. And the answer is all of them. I'll show you how to figure out what to do with each hand you have at the table in your head in seconds.